In this video, we're going to discuss how to define sine and cosine using the unit circle. In particular, we're going to define the sine and cosine functions for any angle using the unit circle, not just for acute angles. We're going to find the sine and cosine of an angle given the corresponding point on the unit circle, and find the sine and cosine of angles whose terminal sides lie on either the x or the y axis. In this video, we're going to take a look at the unit circle and how we can use it to develop the 6 trigonometric functions so that those functions can be defined for angles which are bigger than 90 degrees. So to be clear about what we mean by the unit circle, we simply mean it's the circle in the plane that has a radius of 1 unit and is centered at the origin. It has an equation, x squared plus y squared equals 1, and looks like this. So our primary goal of using the unit circle is to develop a way to define the trig functions for all angles, in particular angles that are not acute. As we've seen with right triangle trigonometry, we can define the trig functions for angles as long as they can be represented as one of the non-right angles in a right triangle, and those are precisely the acute angles. So the sine or cosine or any of the other trig functions cannot be defined using right triangle trigonometry for any angle that is not acute. So to do this, let's actually start by looking at an acute angle whose sine and cosine we know, and see if we can figure out how to relate the sine and cosine of the angle to the unit circle. So let's take a look at the angle 30 degrees or pi/6 radians. So I've graphed it here in the unit circle in standard position, so the vertex is at the origin and the initial side is along the positive x-axis, and I've roughly drawn the terminal side here at a 30-degree angle. What I would like to do is I would like to find the coordinates of this point here that I've drawn in blue, the intersection between the terminal side and the unit circle. And we know it has two coordinates x and y. So we'd like to figure out what these two numbers x and y would be for this particular angle. We can find the y-coordinate of this point using a little bit of geometry. And what we need to do is create another angle of 30 degrees, but in the other direction. So I'll do that here in green. And so this angle here is also going to be 30 degrees. We notice we have another point of intersection here, and I'm going to connect those points of intersection with a line segment. And in doing so, I have formed this triangle right here in green. The central angle in the circle is 60 degrees because it's formed by two 30-degree angles. And the other angles in the triangle are also 60 degrees because the side on the right-hand side of the triangle intersects the x-axis at a right angle, forcing the other two angles here to be 60 degrees. And therefore we have an equilateral triangle. Remember, this is the unit circle, so I know that these two sides, which are radii of the unit circle, must also be length 1. And that means this side over here, the third side, must also be length 1. Well, what I really want is this length here. This would be the y-coordinate of my point xy that I want. And since this triangle is symmetric over the x-axis, this needs to be equal to 1/2 because it needs to be half of 1. And so that tells me that my y value for this point here is 1/2. And now that I know one of the coordinates, to find the other, we can use the equation of the unit circle because we know this point xy lies on that circle. So we know x squared plus y squared has to equal 1. That is the equation of the unit circle. And we know that y is 1/2. So x squared plus 1/4 is going to equal 1. We subtract 1/4. So x squared is going to equal 3/4. So x is going to equal plus or minus the square root of 3/4, which is square root of 3 over 2. Now, our point that we're looking for here is in the first quadrant, which means that we want a positive value of x. And so for our point here, we're going to choose the positive square root of 3 over 2. So this point that we were looking for, x comma y, is the point square root of 3 over 2 comma 1/2. Now what's special about this point is that in relation to the angle that we started with, 30 degrees or pi over 6 radians, these two numbers should look familiar. In fact, square root of 3 over 2 is the cosine of 30 degrees, and 1/2 is the sine of 30 degrees. And so this point where the terminal side of the angle intersects the unit circle gives us as its coordinates the cosine of the angle and the sine of the angle. And you might think that this is sort of a fluke that happens with this particular angle, but if you did a similar analysis for a 60-degree angle or a 45-degree angle, you would see that the point where the terminal side intersects the unit circle gives us the same thing. The first coordinate would be the cosine of the angle, and the second coordinate will give us the sine of the angle. And so, in general, if theta is an angle that's in standard position, again meaning the vertex is at the origin and the initial side is along the positive x-axis, and xy is the point of intersection between the terminal side of theta and the unit circle, then sine of theta is going to be the y-coordinate of that point, and the cosine of theta is going to be the x-coordinate of that point. Notice that this is any angle theta. This does not need to be an acute angle. We just saw in this example that for 30 degrees or pi over 6 radians, this definition aligns with what we already saw using right triangles. And this is the case. If theta is an acute angle, we can use either the unit circle or the right triangle approach in order to find the sine and cosine, and these values will be exactly the same. The benefit of this approach is that here theta can be bigger than 90 degrees or even negative, and we can compute the sine and cosine just as well. So suppose for an example, we were given the angle theta in the picture here on the right, and notice that this angle is not only not acute, but it is actually bigger than 180 degrees. It's bigger than a half rotation. All we know about this angle is that the terminal side will intersect the unit circle at the point -3/4, -7/16. And so we'd like to find the sine and cosine of this angle. Given the size of the angle, we'd have no way to do this using right triangles, but using this unit circle and the definitions we've just seen for sine and cosine, we can do this easily. We know that sine of theta is the y-coordinate of that point of intersection, so in this case, -7/16. And we know that the cosine is the x-coordinate of that point of intersection, which is -3/4. So once we have this angle given in this way, and we know that point of intersection, there's really no work in writing down the sine and cosine. It's simply remembering which is the x-coordinate and which is the y-coordinate of that point. Of course, the difficulty comes in these types of problems by actually having to find the coordinates of that point. Ordinarily, they're not as nicely given to us as they are here. But when they are given or when we can find them, finding the trig functions are quite simple. In this example, we'd like to find the sine of 0 and the cosine of 0. We wouldn't be able to use right triangles to do this because we cannot have an angle of 0 degrees or 0 radians in a right triangle. And so we have no choice but to use a unit circle approach to find these values. So we'll start by looking at a unit circle and looking at an angle which is 0 radians or 0 degrees, which is a very simple angle to draw. This angle will have the same initial and terminal side, and both will coincide with the positive x-axis. In order to use the unit circle to find the sine and cosine of this angle, we need to look at the point where the terminal side intersects the unit circle. From this picture, we see that that point is point 1, 0. It's 1 unit to the right of the origin. And sine of 0 is defined to be the y-coordinate of that point, which is 0. And cosine of 0 is defined to be the x-coordinate of that point, which is 1. And so we get a sine and cosine value of 0 and 1, respectively. An approach similar to that used in the previous example can be used to find the sine and cosine of other angles whose terminal side lands on either the x or y axes. In particular, angles of 90 degrees, 180 degrees, 270 degrees, and 360 degrees can all have their sine and cosine evaluated by looking at the corresponding point on the unit circle and looking at the x and y coordinates of those points. If you'd like some practice, try filling in the rest of this table using that approach. The answers will appear in a few seconds. Notice that the terminal sides of all of these angles intersects the unit circle at points whose coordinates are either 0 or plus or minus 1. Also notice that 0 degrees and 360 degrees have the exact same sine and cosine values. This should not be surprising because the terminal sides of those two angles are exactly the same. In both cases, the terminal side is the positive x-axis. The only difference is the way that the initial side was rotated to end up at the same position.